Welcome to another lesson in our series on probability. In the last lesson, we looked at a way to calculate probability by counting the number of favorable outcomes out of the total number of possible outcomes. But here's another interesting thing about probability. In the investigation with the socks, we had 3 socks, 1 navy and 2 white, and we made sure that each sock had the same chance of sinking to the bottom of a tub of water first. So that means the navy sock had 1 in 3 chances of sinking to the bottom of the tub of the water first. But Jared and Refilwe did 10 trials to see which sock would sink first, and the navy sock only sank to the bottom first 2 out of the 10 times. This doesn't fit the 1 in 3 chances we gave it. The number of times the event actually occurred is called its relative frequency. So in this experiment, the navy sock had a relative frequency of 2 out of 10. This is quite different from the theoretical probability of 1 in 3 that we found before. So, in this lesson, we will compare the relative frequency of an outcome with the probability of an outcome. By the end of this lesson, you should be able to define relative frequency, explain the difference between theoretical probability and relative frequency, and work out the relative frequency in an experiment. Jared and Refilwe are about to play games. As with most board games, they start by deciding who gets the first turn by throwing the dice. By the way, the correct term for one of these little cubes with numbers on it is a die. The term for 2 or more of these cubes is dice. But nowadays, most people use the word dice to mean 1 dice or lots of dice. So, we're going to follow the crowd and use the plural form for the singular too.
Okay, first one to throw a 6 starts.
But why always a 6?
Because 6 is the hardest number to throw on a dice. Everyone knows that.
That's rubbish.
Really? Have you noticed how often we've thrown the dice and it hasn't been a 6 yet?
That proves nothing. I mean, it hasn't even landed on a 5 either.
True. But you know what? Let's find out more about this. Let's ask people who we see and see what they think.
I don't think that'll prove anything either, but hey, let's give it a try.
Excuse me, ma'am. Could you give me a quick answer to a question?
Sure.
What's the hardest number to throw on a dice?
That should be a 6, I think.
The hardest number to hit on the dice?
Yes.
I reckon they're all about the same.
Let's see. I think it's a 6.
I don't know. Any number, I suppose.
Definitely the 6 if you're aiming for it.
It's a 1.
Look at this. Out of 50 people we asked, 41 say they know that a 6 is the hardest number to throw. Are you convinced now?
No, because it doesn't mean that 41 people know that 6 is the hardest number to throw. It just means that 41 people think or believe it. I reckon we can work this out mathematically.
Refilwe and Gerard have uncovered a very popular myth that a 6 is the hardest number to throw. But what is the mathematical probability here? What is the chance of throwing a 6? Well, we need to start by asking, if I throw this dice, what could it land on? Well, it could land on a 1, a 2, a 3, a 4, 5, or a 6. This means that there are 6 possible outcomes. Each outcome has an equally likely chance of occurring, as nobody has deliberately weighed the dice to fall on any particular number. We're trying to find the probability of throwing a 6. So we can put throwing a 6 in brackets after P for probability. We know that the number of possible outcomes is 6, but only one side of the dice has a 6 on it, so there's only one chance of getting a 6. That means the number of favorable outcomes is 1. So the probability of throwing a 6 is 1 out of 6. We call this the theoretical probability of throwing a 6. Now, we want to compare this to the probability of throwing other numbers. In other words, we need to know if the probability of throwing a 6 is higher than the probability of throwing any other number. Every time you throw the dice, there are 6 possible outcomes. So the denominator, which shows the total number of possible outcomes, will always be 6. And each number only appears on the dice once, so there's only one chance of getting a 5, a 2, a 4, a 1, or a 3. So every time the number of ways of getting the favorable outcome is 1. This means that the probability of getting any one of the numbers is always 1/6. So theoretically, the probability of throwing a 6 is no greater or smaller than the probability of throwing any other number.
We threw the dice 6 times, right?
Right.
If the probability of throwing a 6 is not greater or smaller than the probability of throwing any other number, theoretically, one of the throws should have been a 1, one of them a 2, one a 3, one a 4, one a 5, and one a 6.
Right. But that didn't happen. See, we got 3 3s, a 2, a 4, and a 1, but no 6s and no 5s.
This is why we call it theoretical probability. What actually happens may be very different from the theoretical probability. They only threw the dice 6 times, so you could say they did 6 trials in an experiment and their results for 6 trials was 0 out of 6. But they did very few trials.
Let's see what happens if we throw the dice 24 times. 24 is 6 times 4.
Okay.
That's a much better idea. The theoretical probability of getting a 6 is still 1 out of 6, or 4 out of 24. So let's see if they get 4 6s.
After all of that, we only got 2 6s.
So their experiment with 24 throws only gave them 2 6s out of 24 throws. That's 1 in 12 throws. That's still quite different from the theoretical probability of 1 in 6 throws. But 1 in 12 is closer to the theoretical probability than 0 in 6.
Let's increase the number of throws and see if we'll get closer to the theoretical probability.
That's a good idea. Let's do lots and lots of throws.
4. 2. 1.
They threw the dice 24 times and recorded the number it landed on each time using tallies.
We threw the dice 600 times and added up the frequency for each number. These are our results.
They did well. Now, can you make a conclusion about the experiment?
So, how do you think we did?
I think the more often we threw the dice, the closer we got to the theoretical probability.
That's it. Look at our table. Each number came up about 100 times.
What they've just worked out is the experimental probability because it's based on the actual number of throws in their experiment. It's also called the relative frequency, the frequency of throwing a 6 relative to the actual total number of throws made. In their experiment, there were 600 trials, and out of those, 100 of them were 4s. So we can say that the relative frequency of getting a 4 is 100 out of 600, which can be simplified to 1 out of 6 or 1/6. Now let's look at the relative frequency of getting a 6 in this experiment. Again, it was out of 600 trials conducted, but this time the number of times the event happened was 111. That's just a little more often than 1 out of 6 times, but still very close to 1 out of 6 times. But not every experiment on a small sample will come out to exactly 1 in 6 throws landing on a 6. As we've seen, if you only throw 6 times, you might not even get 1 6. So the larger your experimental sample is, that is, the more times you throw the dice, the closer the experimental probability gets to the theoretical probability. So experimental probability, or relative frequency, is the probability we get when we test something out and record what happens in a real situation. It can also be written as a ratio or fraction, but then we record the actual numbers we get from the experiment. The relative frequency of something happening is the number of times the event happens out of the total number of trials conducted. Compare this ratio with the ratio for theoretical probability, the number of favorable outcomes out of the total number of the possible outcomes. Now that we've looked at the relative frequency and experimental probability, let's get back to the chances of throwing a 6.
Well, with our experiment and by calculating the theoretical probability, I think we've shown that it's not harder to get a 6 than to get any other number.
But then, why do so many people think it's so hard to get a 6?
Jared's come up with a good question. So let's think about it this way. The probability of getting a 6 against the probability of getting each of the other numbers. But what's the probability of not getting a 6? There are 5 other numbers, so there's a 5 out of 6 chance of not getting a 6. That's why people say it's hard to get a 6. There's a much bigger chance of not getting a 6. Now, I want you to look at a probability in another situation. Just before the elections in a country, people make predictions about the way they expect the vote to go. These predictions are not just wild guesses. They are carefully worked out based on surveys done. It isn't possible to ask every person in the country who they will vote for, so a random sample of people is asked and the results are used to estimate the possible results for the whole population. Let's suppose a sample of 1,000 people is asked which party they will vote for. About 600 say they'll vote for the Purple Party. 600 out of 1,000 is 60%. So the survey predicts that the Purple Party has a 60% chance of winning. This relative frequency is an estimate of the probability. The bigger the sample of the population that is used in the survey, the more closely the results will predict what the vote is likely to be when the whole population votes. This shows us that probability can be used in real situations to help us make predictions. Now, let's summarize these ideas. Theoretical probability is the ratio of the number of favorable outcomes to the number of possible outcomes. Relative frequency is the ratio of the number of times an event actually happens to the number of trials conducted. It gives us an estimate of theoretical probability. The more trials you conduct in your experiment, the closer the relative frequency will get you to the theoretical probability. Here's a challenge for you. There's a very popular Nigerian game called Igba Ita. Igba Ita means pitch and toss. 2 or more people can play this game. Each person starts with 12 of these shells called cowries. Incidentally, they used to be the currency used for trading in ancient Nigeria. One person is the challenger. The others agree on the number 1, 2, or 3. They each place this number of shells into a pot. The challenger throws 4 of his or her own cowries. They count up how many land with the opening up like this, and how many land with the opening down like this. If they all land with the opening up, or they all land with the opening down, or 2 land with the opening up and 2 with the opening down, then the challenger wins all the cowries in the pot. The other players must decide again how many shells to put into the pot, and the challenger plays again. But if none of these possibilities happen, then the challenger has lost and also has to put the 4 cowries into the pot. For example, if 1 shell lands with the opening up and 3 land with the opening down, then the challenger has lost and another person becomes the challenger. When a person runs out of cowries, she or he is out of the game. The winner is the person with the most shells at the end. Let's watch some people play a couple of rounds so you can see how it works. The chances of 1 cowrie shell landing opening up or opening down are equal. Without working anything out yet, would you choose to be the challenger in this game? Do you think you have a better chance of winning shells as the challenger? Or do you think you are more likely to get one of the combinations, which means the challenger loses? If you discuss the chances in the game with your other learners, this will help you with the task for today. First, work out the theoretical probability of getting a winning combination of shells. Here's a tip to help you in your calculations. How many ways can a challenger get each of the winning combinations? Think very carefully about this one. Secondly, play the game with friends. You can use shell-shaped pieces of pasta to replace the cowrie shells. Record the relative frequency of getting a winning combination of shells. For those of you who want to know more about those shell-shaped pieces of pasta mentioned in today's task, this is what they look like. And you can find them in most supermarkets countrywide. Enjoy the game, and I'll see you next time.